So we have pleasure to have Professor Tilman Plehn today. Professor Plehn has initially planned to come here to spend time with us during this workshop, but and we all were very excited about it. He was also very excited. But however, at the some last minute development, he had to cancel the trip. And however, we are very grateful to have him here. And he agreed to deliver 2 lectures actually during this meeting and workshop period. With his vast experience and wisdom in this working in this area of FML. So he has a illustrious academic journey, starting from PhD in Daisy and then University of Wisconsin, Madison, then CERN Theory Group, also Max Planck Institute in Munich, and he joined University Edinburgh. Before moving into the Heidelberg University in 2012, he is professor there at the Theoretical Physics Division at Heidelberg University. He is also a member of Cluster of Excellence in the Fundamental Physics. His research interests include actually several areas of particle physics, quantum field theory, cosmology. He is particularly known for his different works in supersymmetry, dark matter, jets, machine learning in high energy physics. He's very highly cited researcher and published over 200 papers in peer-reviewed journals. He is a well-known speaker. He came earlier in ICTS to deliver lectures. At this point, his talk is machine learning for LHC theory will be extremely beneficial for all participants, since they have already gone through many of these concepts, tutorials, starting from the preschool. So thank you, and let's start this talk.
Yes, first of all, thank you for having me. It's great to give this talk. I would have loved to come to ICTS, but the problem that occurred to we have to defend a big grant, and you can't imagine how many rehearsal sessions in person and the remote, even people my age have when it comes to defending big grants. So I can't go away right now. So that's a little bit of a problem. Hopefully it's going to be good news when we get the grant. And then I would really like to come back to us ICTS, because I just said, last time I was there, it was all a little bit of still a construction site, but it was clear that it would become beautiful, and I hear it is beautiful. So I hope you're having a great time there. Yeah, I'll talk a little bit about machine learning for LHC theory, where I can emphasize the theory aspect, because I noticed that most of your other speakers are actually experimentalists, and that is perfectly fine. But I want to kind of make the point that also in LHC theory, or not just LHC, in theory, theoretical particle physics, machine learning is a tool that helps us do things that we couldn't before. Yeah, just for my interest in machine learning, I've always been kind of a more numerical person. I've always liked my coding and my numerics, and independent of the general fashion of machine learning that we're observing right now, I think it's important to recognize that you can consider machine learning just as a modern numerical toolbox. So if you want to do modern numerics, you want to be fast, efficient, and precise, you can just check out all the concepts, all the ideas that float around in the machine learning community, and then you can pick some of those. And that's what I'm going to talk about. I have 2 talks, as you already said. This one here, I think of is more introductory, the school is relatively young, so more introductory colloquial style, and then the second one will be more specific, actually with formulas and things. Very few formulas today. Instead, what I start with is something that is really important. It sounds trivial, but it is really important, and that is, if we do machine learning as particle physicists, theory or experiment, doesn't matter. If you do machine learning as particle physicists, we have to always remember that we are particle physics people. We are not machine learning people because we are not machine learning professionals, but we are particle physicists using machine learning, and I will show you later that particle physics problems require a certain kind of machine learning, certain aspects of machine learning, which are not something you can just like get off the shelf. Which means the kind of machine learning we need to do for particle physics is very specific, and essentially we have to like develop some of the concepts, or like further develop some of the concepts that our machine learning friends give us. I should also still think like, all the stuff that I'm telling you is largely, started largely from talking to machine learning people here at Heidelberg University who are not actually particle physicists. So why am I a particle theorist or particle physicist? Well, I'm a particle physicist because I want to know what dark matter is. I want to know why there's more matter than antimatter in the universe. So like, how did baryogenesis happen? And I want to know what the origin of the Higgs field is, right? Like I want to know how the Higgs field came to have a potential, like, or live in a non-trivial potential. As I said, that is important to remember, like, because you can all get lost in, like, we can all easily get lost in all the exciting developments in machine learning and forget what we actually are there for. We're there to understand fundamental particles better. And there's a couple of questions that the LHC, for instance, will hopefully help us solve. Okay, so talking about the LHC, like, let's think a little bit, what makes LHC physics the kind of like physics it is, and so like, lets us benefit from machine learning. The first one is nothing to do with machine learning, but very important to attract the best students. We're asking fundamental questions. Dark matter is a fundamental question. I want to understand, like, what the Lagrangian is that describes the interaction of fundamental particles. The second thing is very closely tied to machine learning, and that is LHC is producing, well, for our experimentalists' benefit, a huge data set. Huge data set means if you actually take Atlas output, CMS output, before triggering, you're talking a few petabytes a second. This is huge. This is even huge by like, industry standards of machine learning, right? Not that we can actually interpret all of that data. Most of it we throw away in the trigger stages, but this is the data set we have to deal with. And then the way we deal with that is we compare what we observe at the LHC in terms of data to first principle precision simulations. And this is something where theory comes in, because unlike in other fields, even unlike in LHCb actually, in Atlas, for Atlas and CMS, the simulations are in the hands of theorists, and we are very, very very much focused on having these precision simulations be based on, say, QCD. So I'm talking about Sherpa, MatGraph, Pythia, Hervik, whatever, or the other event generators, for instance. And what makes us unique in working with this data, and also in the machine learning environment, is that we have complete control over all uncertainties, and that includes experimental uncertainties, statistical nature, systematic nature, even theory uncertainties, which are not even properly defined if you think about it. What is a theory uncertainty? But like, we have complete control, or we attempt for complete control over them, and that is kind of the guiding principle of how we actually use machine learning and particle physics. We have had a very successful past. So like, we have, for instance, measured cross sections, like, and sometimes discovered new particles in the cross sections. People have done, and I'm an old SUSY guy, part of my job, I guess that was in the 90s, early 2000s, was to look at models and suggest to experimentalists what kind of analysis might be useful. Unfortunately, admittedly, my SUSY ideas have not actually triggered any great discoveries yet, but who knows what's going to come in run 3 and run 4. And then also, I think that's, of course, the defining thing of the LHC, the kind of model-driven Higgs discovery, in the sense model-driven that we knew exactly what to look for. I mean, the only parameter of the standard model Higgs that we didn't know was the mass, right? For a given mass, we could even calculate the width. We really knew every property of that particle except for the mass. So, we could guide our experimentalist friends very, very closely where to look, which channels to look, which signatures to look into. As a matter of fact, LHC was to some level built to discover Higgs to gamma gamma. Okay. The role of theory in this entire game is, as I said, the first principle, precision simulations. First principle starting from a Lagrangian, and then precision means calculating, scattering, using quantum field theory, perturbative quantum field theory to, I don't know, what third loop order by now, like, really, really precisely. And then we simulate those collisions. And then we do all kinds of like non-perturbative stuff, pattern densities, hadronization, all these kind of things. Then we simulate the detector, and then you can really think of what we're producing as LHC collisions in the virtual world, where like, the virtual world is defined by a Lagrangian. And this is usually a concept that is actually very easy to understand by people who don't do particle physics. And now, if you have these collisions, you can think of, because how do I look for new physics? Because I want to look for new physics. All physics is boring physics, right? I want to look for new physics. And the way you do that is you compare these simulations and the data systematically, not just some phase-space region that, like, some of my SUSY model might prefer, because, my SUSY model might just not be there. Like, we do that systematically, and then we infer the underlying theory. We learn what the underlying theory is, and then it's either standard model, which I would consider a little bit of bad luck, or it's some new discovery, which is, like, what we all hope for. But you know what? I mean, I don't know what's in the LHC data set. I don't know what nature has prepared for us. So let's be serious about it, understand the data systematically, and we'll see what's in there, right? Automatically. And then, by the way, as a side remark, we're going to come back to that at the very, very, very end. We want to publish useful results or usable results. So like, we want to publish results, and that is the next step for, like, towards 1.3 and 1.4. We want to publish LHC results in a way that, for instance, theorists like me can use it, which is right now arguably a little bit of a weakness of the LHC experiments, because you can't really try to, like, look at Atlas and CMS data without having Atlas and CMS people on the team. Any case, so this is lots of, like, data science questions. What's the role of theory in this? Again, I said, this is like my simulation chain. We start from a Lagrangian, you compute scattering and decays, QCD radiation, like, for instance, QCD effects, pattern shower and fragmentation becoming still QCD dominated by less and less perturbative, if you think about it, then detector simulation, and then you have these events. So we start from a Lagrangian, you generate Feynman diagrams, you graph, for instance, you compute amplitudes and on and so forth. And all of this is theory. And the important aspect, like, that we can't emphasize often enough, because it makes us to at some level unique, maybe not 100% unique, but, like, sets us apart from most fields of, like, data-driven science. You're doing simulations, not modeling. Modeling is, like, modeling the data means I can, like, encode it in a numerical framework. Simulations means I start from first principle, understand what's inside. Looking towards high luminosity LHC, with this approach, like, our job as theorists, what we need to do, we have a problem. And the problem is that high luminosity LHC will have a factor of 20 or 25 more data than 1.2. So that means we're going to look at a huge amount of, like, of integrated luminosity that we need to analyze. And that means we also need to simulate this, like, 25 times as much data. And that's going to, like, be very, very tricky in terms of the resources we have and the technical methods we have. In addition, like as if that wasn't bad enough, the final states that experimentalists can look at are becoming more and more complex. And they're becoming more and more precise, which means you have to simulate more final state particles in higher loop order, for instance. And that is theoretically expensive. Like, because in perturbation theory, higher loop orders are more complicated integrals, even if you can calculate them, are numerically more expensive to calculate. Right? So it costs you more time. Every loop order is, I don't know, is what, at least a factor 10 slower than the previous one. In addition, we also want to cover a huge amount of parameter space, right? Because we don't know what we're going to look for, right? I mean, we are looking for BSM physics, sure, but, like, what am I looking for? So I need to cover the entire parameter space. And I have to enable analysis reinterpretation. After I'm done with analysis, 3 years later, somebody will want to look at the results and compare their model to it, and then there has to be a way to do this. So all of this combined makes, well, it depends, like, if you look at this naively, it makes the high luminosity LHC a theory nightmare, because it's just, like, tough. And then you have to think about what I'm going to do with this. Like, how can we turn this nightmare into something that drives some constructive research? And that actually led me to look at machine learning. Okay, what's LHC specific when we look at, like, machine learning? Well, the first thing is SBI, simulation-based inference. Simulation-based inference, you hear more about that from other speakers, is basically this comparison of the simulated and the measured data set is actually conditional on simulation. The S is you need these theory simulations, which means we have to provide them, like it's our job to do this, right? Understanding LHC data is quantum field theory. Again, that's a job for theorists. Understanding LHC data is not modeling, it's fundamental quantum field theory, perturbative quantum field theory is QCD mostly, a little bit of electroweak stuff, right? So, as I said, the other thing is computing speed means precision. That's good news because we only have to work on one thing. Like if we work on speed, we get precision. Well, modulo, the part of our field that actually, like, you know, calculates higher and higher loop orders and actually has to work on those in terms of quantum field theory, amplitude structures, or like, you know, algorithms. But that's something I'm not going to cover here. What's important is when we do this kind of thing, we need to have control over these simulations and our predictions. And that includes the uncertainties. And if we manage to do this, there's one thing that plays in to our advantage. And this is something that we tend to forget. But if you think about it, like, you know, I just taught theoretical physics 1 and 2, so the first year students, and you think about what are the two things that describe LHC events? You could argue that these are things which already appeared in your first year physics studies, symmetries and phase space. So if you understand symmetries and if you understand phase space means really a bunch of particles produce energy momentum, right? Then we can understand LHC results in terms of symmetries and phase space. And that's kind of cool because it actually means that all our, like, you know, years of studying physics make a lot of sense when you think about our everyday research. Now, all of this is kind of well defined and so on from a physics perspective, but none of this is standard AI, right? The phase space, to begin with, the phase space are symmetries, right? I mean, in standard AI, it's really not clear what kind of symmetries you deal with. Sometimes there are, like, you can guess some, but, like, you know, nobody in AI has the kind of symmetry set that we have. Second thing is, like, you know, everybody thinks about like feature spaces in machine learning. In almost all LHC applications, feature space is phase space. I know what phase space is. I know, like, you know, what an invariant mass and so on and so forth. I know the symmetries. I know it's, like, you know, what a Lorentz transformation is and so on and so forth. So that is our, like, you know, great hope that we can use the interpretability of phase space and our knowledge about symmetries and all of these things, our quantum field theory knowledge, and our, like, you know, ability to control uncertainties to do something also cool in machine learning. Okay, for this first talk, let me just, like, run you through a couple of machine learning applications, which I think personally are very, very cool. Like, you know, it's like a bunch of applications, which I personally like. It's my personal selection. Most of them are going to be theory. You're going to hear, like, you know, you have lots of experimental speakers, colloquial speakers I noticed, and also of your lecturers. So, like, you know, ask them about more of them. And one standard application that, like, I think, like, you know, everybody who does machine learning, like, you know, starts from is jet tagging, or actually, if you want to have it very easy, is top tagging. Why top tagging? Well, because top quarks are very different from QCD quarks. Top jets are very different from QCD jets or quark or gluon, like quark or gluon jets. They are theoretically super well defined, they're experimentally well defined, you know, they can be easily distinguished and so on and so forth. So, like, it's kind of the hello world of LHC machine learning is writing a top tagger. The other thing is that if you write these kind of, like, top taggers and you look at machine learning top taggers, already, like, you know, this, like, little document, I think it's from 2019, already there it was clear that in the task like top tagging, your machine learning methods will outperform by a huge amount everything that's out there. And this is because it's a standard machine learning task. Lots of information, lots of, like, you know, like features, clearly well-defined hypotheses, a classification problem that is actually well-defined in machine learning, so you can just do it. Interestingly, when we did the first, at least, attempt of this study, we noticed that this was true for all kinds of machine learning network architectures. Language models, language-inspired models, image-inspired models, physics-inspired models, symmetric models, whatever. Like, you know, they all did well. So, like, I'm showing you this one figure here, and you see that, like, you know, all of them did similarly well. There's just two lines which were not so good. You see the bottom line, LDA, that's because that was actually anomaly search. That is a totally different search strategy that had never seen top quarks. And then the second one, okay, I should stop saying that, but the red dashed curve, that was at the time the Atlas state of the art. So Atlas didn't want to do this. So we had to bring in a student to actually do the Atlas analysis. By now, of course, in Atlas and CMS, the performance is infinitely better. I assume that you learned some of this from Sunmai's lecture already. And then you're going to have Jan Kieseler's talk on that, he's an expert on jet taking. But that's an experimental task. One of my all-time favorite papers in machine learning that actually I always mention, not only when Sunmai is giving his lecture, is particle flows. So this is the combination of all the data that defines a jet, or actually it works for all kinds of particles, but especially critical for jets. So how do I collect information from the tracker, from the calorimeter, very different resolution, so like tracking is high resolution, but only for particles which are charged. Calorimeter is relatively shitty resolution, but it covers all particles. So how do I combine this? How do I and how do I extract a vector or an n-tuple of particle properties from that? This thing is called particle flow. And it's again one of these aspects where it's clear machine learning is going to beat every standard analysis method. Ask Sunmai for more details because he's an author of this all-time favorite paper of mine. It's outstanding. It includes, by the way, which I think is especially cool, a concept called super resolution networks, generative super resolution networks, which are, if you ask me, very close to magic. The question, can you actually take two images? And normally what you do is you combine two images at the lower resolution, so you downsample one of them. But on the other hand, what you can do is with the neural network, you can actually combine them at the high level resolution by upsampling one of them, which is an extraordinary concept. And that we owe this to machine learning. You cannot do this, as far as I know, without machine learning tools. But a little bit more towards theory. So yes, I want to identify jets. I want to be able to say what a top jet is, what a bottom jet is, ideally, eventually, maybe even what a quark-gluon jet is, even though in quantum field theory, that distinction is a little dodgy. But you see, what I really want to do is also, I want to tell the people who look, for instance, claim that light dark matter can be produced in jets, that you can find those as well. Now, it's very hard because these dark matter jets have hidden value models, they're called. They have a huge parameter space. It's very, very hard to look for them systematically. So what you should rather do in that situation is you should do an unsupervised training. So you basically should try to find jets which are not standard model or not QCD. And for for those, we use so-called autoencoders. And I can refer to Tamo's talk later, next week. He'll tell you more about that, and we'll have also a tutorial on this. Tanmo is in our group here in Heidelberg. Then you cannot ever talk about machine learning without at least mentioning that machine learning has been a standard in LHC physics from the first day of LHC data taking, and that is because the parton densities are produced by a bunch of different groups, and one is called NNPDF, and NN stands for neural network PDF. So anybody who said we will never use machine learning because it's a big fat black box, you can ask, okay, what do you think NNPDF stands for if you don't want to use machine learning? And NNPDF is especially extraordinary, really, when you want to learn how you can control uncertainties. The task is a regression task in essence, but if you want to look at how would physicists control uncertainties in a neural network setting, look at the NNPDF or M3PDF papers. It's full blast. It's amazing work. Just read those papers. Just a little fun fact, NNPDFs have used machine learning so early in the development of machine learning that the original code was written in Fortran by Stefano Forte and his collaborators. But now, of course, this is all cutting edge machine learning. Okay, as a theorist, I already told you, one of the things that I care about is symmetries. Symmetries are lots of them. What I mean, a jet. Think of a jet. What are the symmetries of a jet? Well, obviously, you can rotate a jet around the jet axis, and nothing much will happen. You can also move a jet around in your detector, and yes, the detector resolution changes, but the physics of the jet doesn't change. It doesn't matter if it's a forward jet or a central jet, a soft jet or a hard jet. The physics is the same. Another symmetry is jet constituents, there's like 20, 50, I don't know how many. You can permutate them and nothing will, it's the same information. Now we're coming a little bit more advanced symmetries is, you know that from quantum field theory perspective, a hard quark radiating a soft gluon, right? The soft gluon is just noise. It does not actually carry any information. Collinear splitting is the same thing. You cannot, from a field theory perspective, tell apart a gluon or two very collinear quarks. So these are quantum field theory symmetries or invariances that we want our jet taggers, our jet analysis tools to know, to understand. And this is some work that we have done or others have done recently, which is called contrastive learning, or for permutations transformer networks. So people have worked on that, and these symmetries allow us to really simplify our representation, latent representation of our information, of our jets. You can go the other way around, and this is a paper that I really like. It's by a friend of mine, Veronica Sanz and collaborators. What they ask is, can I maybe discover symmetries? So maybe I don't know all. I mean, I personally think I know all symmetries that happen in the LHC, but that might not be true, like super symmetry, for instance. But more seriously, are there symmetries in data sets that I haven't considered? I don't know. In that case, they have some nice machine learning approaches that they tested on paintings, Van Gogh paintings or Picasso paintings. So asking the question, which is funny, is are there rotational symmetries in any of these paintings, or is there a Z2 symmetry in these kind of paintings? Really cool paper, read it, great fun, again, something you couldn't do without machine learning. Something that I recently learned, by the way, one of my papers is, that in quantum field theory, loop calculations is all about calculating integrals, right? I mean, we do essentially always calculate integrals. Calculating integrals is numerically expensive, right? Because we use Monte Carlo, integration methods for that. Machine learning can actually do something that is very, very different, and it's very cool. So you can learn an integrand, and differential networks, I think you're also going to have a lecture from Tommaso Dorigo. So you can learn the integrand, and then, primitive, it should be primitive. And then you can take your neural network representation and compute from the neural network representation the primitive, not the derivative, the primitive of your function, and then you have a novel machine learning integrator. I think this was written as a code called AutoInt by machine learning people a few years ago, and there's a really nice paper by Daniel Metra and collaborators from Durham showing how you can use that to calculate two-loop integrals. Right? So again, machine learning, new stuff, something we couldn't do before, right? Something we did along the same lines. Think of complicated integrals. A lot of integrals actually because of function theory, you integrate in your momentum space around a certain path. Remember that you have to walk around the poles and stuff like that and do these kind of things. If you think about, we always write down, we integrate a certain path somehow, but we never very specific about how exactly that path looks. We always say, well, it goes around this pole in this direction, epsilon, and then up here and then up and around, right? Something like that. In practice, that's not sufficient. But if you want to do the numerical integration, the shape of the path makes a very big difference. The shape of the path is just a reparameterization. A reparameterization is a mapping that you can actually easily train a network to do. Right? Again, take the network, minimize the chi-squared, the variance of the network, the numerical integration, change the path. You can get a better integration. Something that is really crucial for LHC, I told you, is event generation. Again, event generation is just phase-space integration. Phase-space integration have to do with proposer functions. I mean, this is an art. An art that makes people like the Mudgraph collaboration and the Sherpa collaboration famous. And both of these collaborations have by now found that using machine learning for all kinds of different tasks, for instance, improving a Vegas integrator or a multi-channel integrator, all of these things can be improved by using machine learning. Improved means faster and more precise. I have a few more examples. I'm going to go through speeding up amplitudes. Well, that is obvious. A one-loop amplitude is expensive. A two-loop amplitude might, for a given phase-based point, take up to tens of seconds or minutes to compute. So it takes a long time, much longer than we can afford. So now, every time you generate a process, you have to do this integral. So why don't these, like, you know, people in Sherpa or Markgraf, or the Tulu people around Ute und Heinrich in Karlsruhe, why don't they just like train a bloody network to publish their two-loop amplitudes as a function of phase space in terms of a network? Because then it's fast. Now, that sounds like a trivial thing to do and a trivial request to have. The only problem is then you go to the two-loop people and they said like, yeah, but also you need an uncertainty estimate and your network has to be precise to 1 per mil. Otherwise, we won't buy it because it's not good enough. Because we work at the per mil level and we don't want the network to ruin this precision. So now you actually look at your network architecture and you will find that most of the networks that we think about actually don't work at that per mil level. They're much more sloppy. So now the task is, find a network that's precise to the per mil level and you can trust it. This is like, you know, really an explainable AI question that you can trust it, right? So like, you know, these are all tasks we can be all working on every day. And these are all tasks where people have written, not just us, like, you know, people have written machine learning papers on it. Invertible event generation, I'll talk a lot about that in a second, but let me just start by saying, like, you know, and I'll talk about this in the second half of my doctorate in a minute. Generative networks are not only the fashion right now in machine learning, they're also extremely useful in machine learning, in LHC physics, and I'll tell you a little bit why. But like, you know, we have been like playing, and these groups have been playing with generative networks, including normalizing flow, diffusion networks, or even transformers, like since the very beginning of like LHC physics. And it's definitely my favorite topic. What I won't talk much about is inversion or unfolding. So normally, when you actually when you simulate events, I told you, like, you know, we love to simulate everything down the level to the detector. However, at that level, after the detector, only experimentalists can properly understand and work with that data set. What if we instead did something different? Instead of using neural networks to describe the detector simulation, so look, to translate events from before the detector to after the detector using a numerical simulation, why don't you use the same kind of networks, saying, like, you know, here's an event after detector, and this is how it would look before the detector. It's a symmetric problem. You can, like, if you can do one, you can do the other, technically, right? You're just mapping distributions onto each other. So like you can do that. It's called unfolding. And the great advantage is unfolding is, by the way, something that we haven't like discovered in particle physics. People have done that, but we can now systematically do it. And that allows us to publish data in a way that theorists can use it just by running Markgraf themselves, without detector simulation, without knowing anything about the detector. That's new. That is like one of my great hopes for High Luminosity LHC, that will actually allow, like, these techniques will allow Atlas and CMS to publish data that we can actually use as theorists. Right now, I can't. I've tried to play with the CMS open data, but boy, that makes no sense. Now, if you want to do proper theory, I don't know, maybe, oh, sorry, oops, right? My charger, waving my hands too much. If you don't want to do proper theory, like, for instance, string theory, then you think about, like, you know, these studies of the string landscape. Like, I don't know what the current, like, dimensionality of the string landscape is. Like, you know, when I was young, it was 10 to the 500. I don't know. Like, you know, it's big, right? You would think walking around the string landscape is probably as horrible as playing Go. Like, in the sense, like, you know, that you can find interesting solutions, do stuff, but there's just no way you can systematically explore this landscape with classical method. So, like, same way that you cannot actually write a classical computer program to, like, play Go. So what you do is you use exactly the same method that the AlphaGo uses, and that's called reinforcement learning. Reinforcement learning is basically the machine learning way to navigate, like, you know, spaces of options which are so large that you cannot explore them systematically, and you can still be successful, and you can still find, like, new islands of possible, like, you know, theory, like, you know, standard model UV completions based on simple arguments that, like, you know, you're normally free, like, you know, gauge structures and so on and so forth. So that's beautiful work. I'm not a string theorist. I can only advertise it. Like, you know, people like Sven Krippendorf, they do beautiful work in this direction. And something I like that like, not every machine learning likes as much as I do. And it's like, this is all nice. Like, it's all nice. Like, we can do numerics and we can be precise and we can run really big codes. However, I have not become a theorist to actually just do numerics and like run big codes, right? Like, my true joy as a theorist is if I can at least approximately understand something with a simple formula. The language I speak as a particle theorist is math and formulas. This is why Taylor series are so nice, right? That you do a Taylor series of something, and yeah, like the final, terms are horrible to compute, and you need them to be precise, blah 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 blah. To understand the physics, the first terms or the fundamental part of the physics and basic physics, the first terms is like what counts. And it's interesting because there's a machine learning as more like an AI tool around. Like there's two tools that you can use to actually transform a numerically defined functions back into formulas. Now, this formula is always like, something that always plays like, precision against complexity somehow. Like, there's always like, some like choice you have to make. But there's some like, there's like some really nice like ideas, some really nice studies in astrophysics and in particle physics on learning formulas called symbolic regression. And of course, this is like, finally the way, like, where we go full circle. Like we start from simple formulas, like, a Lagrange, and we compute extremely complicated stuff for the LHC. And then I want to come back to the formula and want to understand things. Yeah, so this is like for a theorist, that's like, of course, my dream, the full circle. So this is just an overview of like, what I think is cool. And I think it's meant for you to like, get some inspiration and say like, no matter what I do as a future particle physicist, even like, formal theorist, there are ways that I can drive my field forward, my field of research, a given field of research. I can drive that field forward by using modern numerics, i.e. machine learning, modern machine learning, right? So there's essentially nothing. There's nothing that like, that is not touched, because everything that is somehow has some numerics aspect is going to be touched by machine learning, because machine learning is just such a great collection of methods. And if the method you're looking for isn't part of the current like, toolbox that's available, well, build your method. Like, take that toolbox that you have and further develop it to build your method, whatever you need to do. All right. So let me talk about my favorite now, like my favorite, part of machine learning, like since, I don't know, for the last couple of years. So as everybody, I started with tagging, but like, even when I did like, top tagging and these kind of things, and I had done top tagging before, I've always been like, a simulation guy. I used to be MudGraph because before MudGraph became too QCD for my competence. And so I used to be a MudGraph guy. So on generative networks, so event generators based on machine learning are my thing. Like, it's what I like most. So let me explain a little bit about those and like, what makes generative networks for the LHC so interesting and so challenging. So what is a generative network? A generative network is a network that generates new images. So it doesn't reproduce stuff like, literally. It generates new images or text blocks these days, like, large language models or LHC events. And the idea is that you have some kind of phase space that could be very, very big. Representation space could be very big, especially for language models. And you encode some kind of a density, probability density there. And then you basically take a known distribution that you can, like a Gaussian or uniform distribution that you can sample from, and you transform this and like, and you sample into your target space, and that you hope what comes out in your target space are these new images or text blocks or LHC events. Yeah. So in that sense, this is all like, the theme of like generative networks is you start by learning a density in some kind of target, in our case, phase space. And then you want to reproduce the training data that defines implicitly this density, but statistically independently. So what you produce in terms of the sample, then that follows the same distribution, underlying distribution, is statistically independent from the training data, physically equivalent. And then, of course, we're physicists, and I want to include an uncertainty on the estimated density. And this is the first problem you're going to encounter, because of all the methods that actually known like for generative networks in a machine learning community, none of them actually even mentions the word uncertainty. But we can't do without. I mean, how I'm going to produce LHC events in Sherpa without having a density, an uncertainty estimate on it. I mean, experimentalists insist in having that, and they're right. So in generative networks, they're essentially in the last, I think we're probably talking good 10 years, they're 4 famous architectures, or 4.5 famous architectures around. The first one you might have heard are variational autoencoders. Variational autoencoders are very, very efficient generators where the defining feature is that you have a low dimensional latent space, actually fundamental physical representation, but then the actual representation is very high dimensional. So think of them as image generators, right? The problem with the variational autoencoders is their precision, because you describe your density through a much lower dimensional latent space. So you have to cut corners at some level. And you should apply them to problems where you know that you can cut corners, because some phase-space regions might really just be noise, like detectors. The coolest machine learning generative network that I think exists are called generative adversarial networks. You'll hear about those, I'm sure, in your school. If you haven't already, these are these game theory networks where you have a discriminator network and a generator, and they play against each other. One tries to trick the other, and at some point, the two of them agree that they have found a good solution that both are happy with. Yeah? So you don't actually have to take a GAN. You don't have to tell the GAN what to do, it knows automatically what to do. A more modern version of machine learning is are normalizing flows or diffusion models. They work very similar, where you, unlike for the variational autoencoder, now your representation space and your your latent space are the same dimensionality. So there is no compression involved. There doesn't have to be any compression involved. And that means you can write a bijective mapping between these two densities, between your, say, Gaussian latent space and your however many modal, whatever it is, phase space. And because it's a bijective mapping between those two, or approximate bijective mapping, you can actually train them especially stably. They're super efficient if you want to be precise about things. And that holds for normalizing flows and diffusion models. They work very similar in many ways. This is a smooth transition from normalizing flows to diffusion models, really. Well, and then the most famous one, maybe the most famous one, well, the one that's in the media nowadays are generative transformers. I won't talk about them much, but I just say, these large language models, ChatGPT, they're called, right, typically, or whatever the other companies have. They're extremely successful in language predictions, and of course, and for LHC events, we have tried them. So if you think you want to publish a paper that's called JetGPT, well, that ship has sailed. We already did. Have a look at it. I personally should say, for me, transformers still have some work to do on the precision frontier. But let's see how far we can push them. What's important now, you have these different models, and now pick one for your purpose in your simulation chain. Like phase-space generators. As I said, LHC physics is phase-space. So what is a phase space? It could, for instance, be hadronic phase, a partonic phase space. It could be anything, could be jets, but take a parton phase space. Z decaying to 2 muons, so you have a narrow mass peak, and then plus 1, 2, or 3 jets. Yeah, this is depending on your count, this is some kind of 20 or less dimensional phase space. So what do we do for those? Well, you look at these recipes and say, okay, 20 dimensions, I don't need a variational autoencoder. I can use a GAN. Okay, we tried that. GANs are not super precise. Normalizing flows or diffusion models work better. So what do we do with those? For normalizing flows, as I said, you have a bijective mapping from a latent space, and these are the only formulas in my talk. From a latent space that's Gaussian to the phase space that follows the data. And the trick of these we call them invertible networks here, and neural networks here, for instance, in Heidelberg, these normalizing flows, is that if they're bijective and you know what the distribution is that you start from, which is Gaussian, you don't have to learn the density here. You learn the Jacobian. You're transforming one distribution into each other, and you encode this information into a tractable, so into a numerically evaluable Jacobian between your latent space and then what becomes your model space. You don't learn the density explicitly, you learn the Jacobian. That's important. Second thing is, what you write down always, almost always for machine learning, like, nicely is the loss function. What you minimize? Well, what you minimize is what you maximize is the likelihood of your model to reproduce the data. Or what you minimize is the negative log likelihood of the data. That is actually literally the loss function. So this is the log likelihood of the model reproducing the data. So you sample over the data and you're looking at the log likelihood of your model. And the negative log likelihood you minimize. This is first principles loss function of a neural network. And you do this here, and what I'm showing here is the PT of for instance, the leading jet in Z plus jet production. This is actually Z plus 1 jet production here, only the plot I'm showing you. And you see that, the network learns this extremely precisely. Right? It learns things to order of 1%. 1% is a pretty good benchmark for the precision of LHC. For GANs, that might actually be hard to reach that 1%, so I'm showing you that. You also saw that you see on the bottom panel that the agreement between data and the model actually gets slightly worse and a little bit noisy if you go to the tail of the distribution. There's a simple explanation for that, and that is, well, I have less training data in those tails. Less training data means my trained model is more noisy. It's as simple as that. Okay. Now, as I told you, I think the coolest networks that you can have are GANs, because you have an extra discriminator handle on your agreement between your model and the training data. And this is actually what we physicists, what we want. I want this extra discriminator. So what you do is you have a generative networks that takes like in the generates space-based distributions or events, and then you have a discriminator, and the discriminator you train to be 1 if it correctly identifies a generated events, like from your model, 0, 1 for the training data, and 0.5 if it doesn't know. So in other words, the perfect generative model and the perfect discriminator will always produce 1/2 for discriminator output. What's interesting is that you can use the Neyman-Pearson lemma, you can to relate the discriminator output to the underlying phase-space density. Neyman-Pearson lemma tells you that the optimal discriminator would learn the likelihood ratio. And the likelihood ratio is nothing but the phase-space distribution. So you can actually translate the discriminator output D into a reweighting function, D divided by 1 minus D. And that reweighting function, if you look at this ratio here, is the function that you have to multiply your model density, the denominator, with to get the data, the correct density out. So if you want to correct your generative network, you basically weigh every event with this W, and you should get closer to the training data by definition of the well-defined, well-trained discriminator. You can use this for 2 purposes. You can use this to control your network, or to reweight your network. And I'm just showing you here 2 distributions, where you can see where the red curve is the reweighted curve. Look at the right-hand side, for instance, the invariant mass of the 2 muons, which should give you the Z mass peak. And what you see is the INN, the flow generator, actually has a slightly lower, slightly broader peak than the original training data, and now which is the green curve. And then now you reweight those events, and you will recover the red curve, recover to at most if 1-2%, 3% the mass peak, right? So you can use this the discriminator after the fact to improve your generative model. This is like a great tool in the hands of a precision obsessed particle theory person, right? I mean, I can now check my generative models. As a matter of fact, if you want an open problem, where you can actually write a really nice paper, and I'd love to talk like anybody who has ideas, is if I can do that, why can I not use the same trick that people use for GANs, namely to take a generator and somehow use a discriminator trained in parallel to improve the training of the generator? Why can I not do this? Well, and the answer is because me and my group, we haven't been able to make it work really. We have an idea where you can do this. We call this we call this disk flow. So discriminator normalizing flow network. And you see it works a little bit better. So if you look at like, these curves here to the right-hand side, this is delta R. This is the angular correlation between two jets and Z plus jet three jet production. And you see here at like, at the collinear cutoff, like, two jets which have to be separated by more than 0.4 units to actually be counted as two jets. You see that our normal, our network isn't doing so well. It's certainly not reproducing the training data, but you see, like, our disk flow here, yeah, I mean, is not perfect, but it's very close to the re-weighted data. So that means most of the information that the discriminator has and that would normally re-weight is actually not already embedded in the training. However, I should say, like, this is that leads to some very interesting questions, like, for instance, with the GANs. Everybody says, like, these GANs, they have this equilibrium. It's a Nash equilibrium between, like, generator and discriminator, where neither of them wins, right? They find a good compromise. There's also lots of papers who say, like, that Nash equilibrium doesn't exist. I don't know. I really don't know. Mathematically, for GANs, it seems to work. What I can tell you is, if you do the same with flow generative, normalizing flow generative networks, the Nash equilibrium seems to not exist. Or at least in our studies, we have never found it. Which means when we train a generator and discriminator with a normalizing flow, one of them wins. And this is not the situation you want. So if you need an open problem, here's your open problem. Please work on it. Please send me an email or write a paper. If you want to target uncertainties now on this with a phase-space density, think about, like, how we target uncertainties in a fit function. What do you do in a fit function, just like a regular minuet fit? Well, if you want the uncertainty on the output, what you do is you learn for every fitted parameter that is in your expression, you learn a central value and an uncertainty, and then you sample through the uncertainties of these fit values, fitted parameters, and then from this sampling you get the output uncertainty of your fitted function. So thanks to Yarin Gal, who's who wrote his thesis in 2016 and is still already famous senior machine learning, cutting edge guy. We know how to do this for the same thing for neural networks. These networks are called Bayesian networks. There's nothing Bayesian about them. It's just they have inherited this, from a particle physics perspective, very unfortunate name. They're called Bayesian networks, but what they are networks that, just like a fit, they learn not only weight value but a weight distribution. As a matter of fact, that you can approximate most of these weight distributions very efficiently through independent Gaussians. That works well in our practical application. Doesn't have to. And then you sample and you get uncertainties on the output. And here's my Z+1 jet PT of the jet distribution back. And now you see that the blue curve, which is the network, has an uncertainty band here on the right-hand side in model over truth. You look at that, and you see that uncertainty increases with less training data in the tail. So that's good news, because it should. And it also covers the one quite nicely, even though, the central value, deviates from one in the tail, but it covers it nicely. So this is the Bayesian uncertainty of the network prediction. So statistics-related error bars can be actually learned by Bayesian neural networks, also generative neural networks. That concept has long been known for regression networks for quite a while in classification. And if you're interested, you can actually extend it quite trivially to Bayesian networks, generative networks, where this uncertainty is the uncertainty on the underlying density that you sample into. And for normalizing flows, you can do that fairly easy. What about theory or other systematic uncertainties? What, for instance, if I know that my PT of my jet is poorly modeled, because there are pseudo-curve logarithms, and for large PT, I have large perturbative uncertainties, and I shouldn't trust my result there. So what I can do there is I can take my training data and I can augment it. So what I can do is I take my training data and I simulate it, taking into account another parameter A that you see here that changes the weight of my events, right? Such that PT of 15 GeV, like, it doesn't change anything, but if you go above 15 GeV, it like, it leads to an increasingly large correction factor proportional to A. And the way you simulate this now to take into account the uncertainties is you train your data and you give your network your phase space information and A, so that your network learns a distribution under the condition of A, a given value of A. And then when you sample, you vary A in the sampling, like, in addition to your Gaussian random numbers, you also vary A in the range whatever you want and with a shape whatever you want. And then your prediction will model exactly that uncertainty that you put into the training data through your data augmentation. So that's at least one way to, like, consider systematic or theory uncertainties, right? So by augmenting the training data. Why is that? For particle physics, why is this useful? Well, because in particle physics, we can typically train stuff on control training data. So here's, like, our little bit advertisement plots. So like what I can do when I like simulate, for instance, Z plus jets, and this is now the PT of the muon. I can get a distribution and it's super precise. And you can see, aside from the left-hand side from tail here, I agree, like my network agrees with the truth to, like, in the bulk of the events better than 1%, and then in the tails to, like, a few percent. I can reweight it. I can use my Bayesian network to look at the statistical uncertainties, and I can use my augmented training data with this A values here, in that case with this PT, to have, like, the theory uncertainties. And now they're over the entire phase, but like everything is correlated. So it's all reliable. The last thing I want to, like, show you is the question that everybody, like, has to answer is, imagine you have a generative network. How good is your generative network? And there's a million, like, measures, like, in machine learning that people use for that. But, I don't care about any of them because I know already what I want to use. I want to use my discriminator. I like, this is what I told you. This is why the GANs are so cool. And this is, like, what is so cool with the reweighting factor. So let me just train a generative network. And then I'll also train a discriminator network. And discriminator networks are easier to train. So that means my discriminator will learn things better than my generator. And that means I can understand how good my network is by looking at the weights, so these correction factors for each phase space point. And I can look at them for each phase space point in the sense that phase space is interpretable. I can just plot them, right? I can just, like, for instance, the easiest thing is I just histogram these weight distributions. And obviously, if there's, like, because then they're similar to differently, I should use, like, evaluate them on the combination of the training data and the generated data, and then typically peak at 1, and then they have some kind of a distribution, as you see here, right? And then you can, like, calculate a width of this distribution, and then you see how precise your network is. The other thing you can do is you can ask the question, like, okay, here I seem to have a large tail. Or to the right, I have a tail, whatever you have, and then you can look for events that come out, or phase space points that have a large correction factor, and then you can check in phase space, you plot them, and you see, like, okay, where is my correction factor large? Like, where are things going wrong? And for instance, for Z plus 2 jets, you can ask the question, where do I have particularly large correction event? Large corrections means where my generated density has to be corrected upwards to actually match the training data. Well, we have a Z peak, I told you, and the Z peak is typically a little bit broader in the simulation. The resolution is fine, it doesn't work that well, which means at the center of the peak, you have to bring things up. Well, you look at a distribution like this here, and you see that this is exactly what's happening. On the center of the peak, my weights have to be large. This is the orange curve. And then where do my weights have to be small? Well, on the shoulders of the peak, I have to bring down the shoulders to make the peak more narrow. That's exactly where these, like, events sit. So if you want to use machine learning methods to check how good your generative networks are, don't take any of these, like, standard, like, you can also take some standard methods. But remember, phase space is interpretable, and Neiman-Pearson lemma tells me that, like, my discriminator actually converges to the likelihood ratio up here. And we have some generative explainable AI just made for LHC physicists because we can just look at them, we understand what's happening. Our great advantage. The last, slide I want to just talk about is inverse simulations. So I told you that a forward simulation takes an event before detector, for instance, and then simulates the detector and generates the probability distribution after detector. This is a conditional probability. A probability after detector conditional on the event before detector. Now, from that logic perspective, given that these are just phase-space distribution, this is not a deterministic system, right? I mean, this is all quantum and interference and stuff, right? From logically, I can just invert this. I can say, okay, if I can train a network to do this in one direction, I can also train a network to take an event conditional after detector and calculate the phase-space probability before detector. If none of these density is 0, in which case this thing diverges, you can do that. It's symmetric. And this is exactly what people want to do. And actually, we know this. People have been talking about detector unfolding. Unfolding to QCD patterns, by the way, is what we use to what we call a jet algorithm. We know this. We do this all the time. But unfolding jet radiation is something I always wanted, because I remember when I did SUSY stuff, we wanted to know which jets are from squark decays and which come from initial state radiation. That's really important for your analysis to sort this out. TT bar Higgs production, extra jets, do they belong to the top, or are they initial state radiation, right? As a global analysis guy, I can tell you the top group in Atlas and two groups in Atlas CMS have been using unfolding, and this is by far the best way to publish data. Tells them the user, I'm a user here, I know. So I know what I should work on, and that is I should work on with my group and with my friends and with Ben Nachman and his alternative way of doing the same thing on getting these inverse simulations. And this is the point where, by the way, I think we're going to make some more transformative progress for the LHC, but I don't have enough time to talk about it. Not just doing things better, but doing things that we couldn't really do before. And that is actually the essence of LHC, theory using machine learning, right? You can say it's just a numerical tool for a numerical field, and great things will happen. There are two advantages. First of all, we don't have to pay for it. And if you look into the amount of research that that is produced by machine learning, it's clear that one field of science could never pay for that. Even academia could never pay for that, right? This is paid for by Google and Facebook and all the companies and OpenAI and Microsoft and everybody. So these are billions going in there, and we can just harvest the stuff that we like. The stuff that we don't like, we don't harvest. We just harvest the stuff that we like. And then we can use them to either improve established tasks, which is something that experimentalists work very hard, but that is admittedly a little bit sobering at times. But maybe you can establish new tools for established tasks, do things really much better. As in event generators, doing things much better than you could ever do them before, right? To deal with a tenfold increase in precision that we need, right? Or you can transform something by new ideas, which unfolding is kind of in between, or symbolic regression, right? And I think what we are looking for, if you think about what we most care about in LHC physics, is something that machine learning people call explainable AI, XAI, because we think of this as precision control, uncertainties, symmetries, formulas, all of these things that we care about as particle physicists, as physicists, who want to understand our data systematically in all detail. In machine learning, in the literature, that's actually called explainable AI. Explainable AI is also a very broad set of concepts, and it's not always used, I will say, sometimes it's a little bit of just a word, not much behind it. But in particle physics, explainable AI is actually our task, our goal. I mean, we want to understand what these networks do, because if we don't understand what these networks do, well, then we can't really use them. Because are we really prepared to use a bunch of things that we don't understand to then claim they're stark matter? Who's gonna give that talk? And then you a year later, chances are you have a Nobel Prize or you look like an idiot, right? We don't want that. We want the Nobel Prize, right? So explainable AI is crucial. Any case, so I gave you an overview, and you're learning a lot about about machine learning. For me, it's a kind of reviving way of having lots of fun with hard LHC problems. If you want to learn more about the stuff that we're doing in my group, we have some lecture notes which you find on our website, Modern Machine Learning for LHC Physicists. it's again a collection of things that either we did and I like, or other people did and I like, or we like. So like, it's a master level course, lecture notes, including tutorials, by the way. So have a look at them. Thank you so much.
Thank you. Thank you, Tilman. So now question session. So let us move and okay, Sanmoy.
Hey, Sanmoy.
Thank you for the great talk. In the context of generative model, what do you see for the upcoming days, like making the 3 to 4 body phase space using GANs more necessary, or just stick with like a fixed particle phase space, but improve the computation time? In which direction this kind of research should go in your view?
I mean, you're correct. So like, when my loop friends make these diagrams, I'm sure probably have seen them. There's always loop order here and like, multiplicity here, or the other way around, right? It's loop order versus multiplicity. Right. So if you want to do 2 loop, I think cutting edge is 2 to 3 or something like that, right? Mm-hmm. And these things are extremely time consuming. There was a nice paper recently, I forget what it was. I think like Michael Chakon and friends. They basically say, like, in the introduction, it's almost impossible to actually generate these things on the fly. It's super, super expensive. So that means for 2 loop stuff, I think 3 particles in the final states are fine, but you have to work on your speed. But 2 loop means precision, right? I mean, 2 loop, a 10% estimate on 2 loop is pointless, right? I mean, it's like, no, these guys, like, 2 loop is all about percent or below percent. On the other side, other end of things, like, and if you look at what is Sherpa doing, people, or like, in MATGraph, what we're looking at is the processes are TT bar plus 1 to 3 jets. And this is leading order or next to leading order. Or like, something that is known for being especially nasty is big boson fusion scattering. So that is 2 forward jets and 4 central fermions. So this is like, a 2 to 6 process. That is very difficult to simulate. So these are like, so that's what I mean. So like TT bar plus jets is like 6 to 10 final state particles. Big boson, big boson scattering is hard process is 6 final state particles plus a bunch of extra jets. So again, 7, 8, 9. And that is leading order needed next to leading order. Is the cut is already helpful. But if you look into 2 loop, I think like, people will look for like just, I mean, if you crack the 3 particle phase space, with sub% precision, then you have your business there. Okay. So it, both directions.
Yeah. Okay. Thank you.
Thank you. Any more questions?
Everybody's a little tired after the day.
After a long day, they had a long tutorial.
Hello, I can ask one question. You mentioned about symbolic regression, which is a new term for me. Could you elaborate a bit on where do you see in HEP the applications of symbolic regression?
Yeah, so symbolic regression, there's 2 groups that are developing these methods right now, by the way, I should say. There's Max Tegmark's group, I think it's called Feynman AI or something, and there's Miles Cranmer with his PICER. Both of them have more like a Cosmo background. But like the thing that I see this in particle physics, and we already looked into this, is think of constructing observables, so optimal observables. Like, you want to define yourself an observable that's especially sensitive to whatever CP violation in the Higgs sector or something, or the Higgs mass in di-Higgs production or something. So imagine you construct yourself a relatively complicated observable that might even only be defined through an algorithmic solution, or you have to ask your Monte Carlo friends and they give you a very complicated, like, complicated expression for an optimal observable. In that case, you can learn. I mean, you have no control over this, right? You don't know. Like you can plot it, but like you have no control. So like it's so much nicer if you could say, okay, given the precision that I need for this data set for my analysis, which is a well-defined question, given the precision I need, here's a formula that does as well as the complicated structure. Let me give you an example. If you look at weak boson fusion Higgs production and you're looking for CP violation in the gauge Higgs coupling, W Higgs coupling, we know that the optimal observable for that is PTZ1 times PTZ2 times sine of delta phi of the two tagging jets. That is actually known. I think Dieter Zettenfeld calculated this a long time ago, several years ago. Now, this is only true to leading order without backgrounds, without detector, blah, blah, blah. So like, this is not strictly the correct formula. But it is like, the starting point. And now you can actually take your simulations and include higher orders, and you can include detector effects. And backgrounds. And now you can actually compute the same optimal observable, but you can put this in as a compact formula in a line and a half. And that's nice because it allows us to look into it, and we can, for instance, check that it should definitely be very close to PT1 times PT2 times sine delta phi. And if it's not, like where do the differences come from? What's changing? Like for instance, there's no rapidity dependence on that, in that optimal observable, and that is correct in principle. However, the detector performance depends on the rapidity. So once you consider detector effects, the rapidity dependence will appear. So, and then these are all aspects you then understand from the formulas, and that makes it so much easier to control. So I see there, but whatever, I'm sure people will come up with applications where you know how to compute something, and it would be nice to have at least an approximate compact formula. But the optimal observable for me is has always been a little bit of a holy grail. And if you want to make it even more complicated, think about the optimal observable for for the Higgs CP for Higgs CP violation in the top Yukawa coupling. And ask my former student Dorival Gonzalez about it. He's written a whole lot of papers about it, with or without me, but mostly without me. And this is a very complex measurement, and maybe we can find a formula to do that. That would be nice, because we like formulas and we can read formulas. I can't read pages and pages of code.
Hello, thank you. Good. From the student side.
Hello. So I just had a query about the problem that you were talking about in this normalizing flows generative and generator and discriminator.
Mm-hmm.
So, generally, when we train a normal GAN, then the generator and the discriminator are usually similarly expressive, right? So if you are doing a CNN, the other thing is more likely a similar this thing. So when you do that, do you actually do both I don't know the underlying details, but are the two networks similarly expressive in terms of function approximation? Because
no, that is the main difference. So the normalizing flows, what they are, and diffusion models are somewhat similar. Normalizing flows are not as expressive, but then think about for phase-space distributions in particle physics, we don't need to be super expressive, right? We just need to describe a bunch of PT tails, delta R cuts, and intermediate mass peaks. This is nothing, right? This is not very, very difficult to do for the networks for functional classes. So normalizing flows are less expressive, but very stable in the training. And I believe this is exactly the problem when we take normalizing flows and combine them with discriminators. So how do I force the two to learn roughly at the same rate? And I'm not saying it's impossible, it's just we never managed.
Oh, thank you.
So I can tell you, essentially think of it that way. If you want to learn them both, you somehow have to couple the discriminator into the generator training, right? Yeah. You can do that with some kind of adversarial, like, parameter, we are basically just like in a coupling parameter. What happens if the coupling parameter is very, like, small, the generator just ignores the discriminator, doesn't matter, right? And then you pull it up, the parameter, you increase it, and then a phase transition happens, and then the generator just, like, just reproduces the discriminator perfectly and doesn't care about the target
So
density.
it has to do with the difference in the ability of the two networks, something like
Yes.
that.
And we never managed to, like, bring them to the same table. Yeah.
Thank you.
And
Another question.
Let me just
Okay.
say one thing. If you do the same thing with instead of normalizing flows, you use this so-called diffusion networks. Diffusion networks are really very similar to normalizing flows in many ways. They are slightly more expressive and slightly less stable in the training. I mean, like, slightly harder to train or take longer time to train. But I think I don't expect this thing to get better with diffusion networks. But somebody please try to convince me of the opposite. You're going to be my hero if you make that work.
One more question here from the student side.
Yeah.
Okay, hello. Thank you for the nice talk. So I have a question on the generative adversarial network distribution that you showed there. So, I mean, you showed one, like, 1D distribution. So, but, we can generate many other properties also, like, many event properties there. So, I mean, there are some correlation also during, between the event properties, right? So, like, how GEONS handles to preserve the correlations between all the variables? Like, there are GEONS, there are VAE or normalizing flow. So, like, which works better to preserve the correlation between the variables also?
Okay, so the diagnostic tool I would use for that is this W distribution and precisely distribution down here. So where you can see, like, this is the weight distribution as a function of phase space, covers all phase space and all correlations, right? It goes into all kinds of phase space directions. So that is not one-dimensional. This is the multi-dimensional test. My experience is that the GANs do fine. Also, VAEs are just not very expressive. I mean, like, they typically fail at some sharper features. GANs work fine, but, sometimes for the GANs, the discriminator and the generator kind of agree that it's fine to ignore stuff, or like that it's fine to be good to 10% on the scale of things. So with GANs, my main problem is that, like, it sounds like such a nice thing to have the discriminator and the generator, like, combined. However, I cannot force them to agree on a good compromise. They will agree on a compromise, but it might be a bad compromise from my perspective. So GANs are kind of hard to force to do the right thing, right? And they do whatever they want. They come out, like, give you something, and either you, like, it's what you want, or, well, you are luck. Flows are, like, much better controlled. So flows will typically learn correlations with some weaknesses, like, for instance, like, like very small and subleading features in phase space. A normalizing flow might just, like, say, okay, fine, whatever. I am limited in my expressivity, so I treat the, like, main features well, and the little features I just interpolate away. Who gives a damn? So this is, like, what flows do, and diffusion networks are a little bit better at that, but not much. If you look into our paper with the GPT, the transformers, if we can convince the transformers to be a little bit more precise and a bit less sloppy and controlled, then I think transformers might be the way out of this. But, like, we haven't cracked that problem. I cannot say that I know how to do this.
Yeah. Thanks. Another more, like, so in terms of, like, generating the discrete variables, are, like, all these models does good? Like, for example, you want to generate, like, number of jet distribution in an event, like kind of discrete, like, variables. So
yeah, so here, like, what we do is to generate the number, like, to look at the number of jets. We actually we do a conditioning on it. If you look into the more recent, like, point cloud generators that people use for jets, Yeah, there's always some like it's always an extra step. It's always an extra step. These point cloud generators, they actually, we have different networks essentially for every jet multiplicity. These point cloud generators, the new ones for jets, they will actually generate the multiplicity distribution, also discrete, yes.
Thanks.
Any more question? I don't see. Okay, after a long day. So, Tilman, very much thank you to you. So it is a very exciting talk, and we'll see you again later this next week.
Yes.
Yeah, thank you very much.
Thank you. And then, yes, see you next week for something a little bit more like detailed after that, like overview. If you have questions, you can also email me questions, and then I will answer them next week. Yeah. So bye-bye.